Hello, professor. My name is Luis Nieto. I'm gonna be doing my chapter 29 exam. Excuse me, I have my voice a little bit weird. I'm sick right now, but I'm good. Right, exam chapter 29. Alright, for this, I choose the problem 29.11. I'm gonna start with part A. For part A, a long solenoid has a cross-sectional area of 3 centimeters squared. The current through the wind is decreasing at a rate of 22 amperes per second. A wire loop of radius 3.10 centimeters is around the solenoid, parallel with its coils, as in center on the axis of the solenoid. The magnitude of the induced EMF is 15.1 microvolts. Find the number of turns per meters in the solenoid. Alright. First of all, we have the given data. We have the amperes. I don't know what's happening. Alright. So, the area, that is 3.00 centimeters square. And that is equal to 3.00 10 times 24 meters square. Alright. Square meters is the same thing. So now we have the rate of change of current, that is di over dt, that's equal to 22.0 amperes per second. Alright, we have the induced EMF, that is 15.0 microvolts, and just passing that to volts is 1.50 10 times negative 5 volts. Right, and then we have the permeability of free space, known as 4 pi 10 times negative 7 Tesla per meter ampere. Tesla meter per ampere. Got it. All right, the formula that we're gonna use is the induced EMF. So it's equal to permeability of free space multiplied by the number of turns, multiplied by the area, multiplied by the rate of change current. So, and we have to rearrange this formula. So the number of turns, it's going to be equal to the induced EMF over the permeability of free space multiplied by area multiplied by the rate of change of current. d1 over dt. Perfect. So let's put the numbers into the formula. All right, it's going to be 1.50 10 times negative 5 over the permeability of free space, that is 4 pi 10 times negative 7 multiplied by the area, there's 3.00 10 times negative 4 multiplied by the rate of change of current, so the top 22. Alright, perfect. Let's get that to the calculator. So 1.50 10 times negative 5 over 4 pi 10 times negative 7 multiplied by 3 10 times negative 4 multiplied by 22, and the answer is giving me 1,810 turns per meter. Perfect. After I'm done with all the problems, I'm gonna go back and check if I did right or wrong. Part B. Find the magnitude of the induced electric field with the loop. Express your answer with the appropriate units. All right, first of all, we have the radius of loop. No, it's 3.10. So 3.10 centimeters. If we put decimeters, 0.0310 meters. And we have the induced EMF, where you know it's 150, 10 times -5 volts. Perfect. The formula we're gonna use is the induced EMF equal the magnitude of the induced electric field multiplied by 2 pi radius loop. Right, since we're looking for the magnitude of the induced electric field, we have to put E equal the induced EMF over the 2 pi radius of loop. Perfect. Now let's put the numbers into the formula. E equal 1.50 10 times -5 over 2 pi multiplied by 0.0310. And we'll get that to the calculator. 1.50 10 times -5 over 2 pi multiplied by 0.0310. And that's giving me an answer of 7.70 10 times -5 volts per meter. Perfect. Now we'll go with part C. Did I put, okay. Yeah. A circular wire loop of radius 0.360 centimeters lies in the plane, the XC plane. There's a uniform magnet field in the y direction that increases at a rate of 0.0150 teslas per second. Find the magnitude of the induced electric field in the wire. Express your answer with appropriate units. Right. Perfect. So the radius, we have the radius that is 0.360 centimeters. We're going to pass that to meters. 0.00360 meters. And then the rate of change of the magnetic field is the V over dt equals 0.0150 teslas per second. These are by meters. All right, the formula we're gonna use is to find the electric of find the magnitude of the induced electric. It's E equal the radius over 2 multiply the rate of change of the magnetic field, so to the absolute, so T. Now we put the numbers into the formula. Radius 0.00360 over 2 multiplied by 0.0150. Let's get that to the calculator. 0.00360 over 2 multiplied by 0.0150. And that's giving me 2.70 10 times -5 volts per meter. Perfect. All right, now we'll go with part D. A long solenoid with a cross-sectional area of 4 square centimeters and 965 turn per meter is oriented with the axis along the x-axis. The field inside the solenoid points the positive zeta direction. A wire loop of radius 5 centimeters is around the solenoid parallel with its coils. Center of the axis of the solenoid and the line in the xy plane. Find the rate of change of the current if this in the solenoid if the electric field in the loop at the point x equal 5.00 centimeters, comma y equals 0, comma z equal 0. Alright, Alright, is the vector of E equal parenthesis plus 1.20 10 times -5 vectors per meter, close parenthesis vector of J. Alright, so we have the given data of this. The radius of the loop is, we know it's 5.00 centimeters. we're passing that 2 meters, 0.0500 meters. We have the number of turns per meter. That is 965 turns per meter. We have the cross-sectional of area solenoid. That is A equal 4.00 centimeters square. And passing that to meters square, it's 4.0010 times -4 meters square. And the electric field, that is 1.20 times -5 volts per meter. So 1.20 10 times -5 volts per meter. All right. The formula that we use here is the electric field formula. It's equal E over multiply perimeter free space multiplied by numbers of turn per meter multiplied by the area over 2 pi r, and then we multiply by the right change in the current, right? Yeah, the absolute rate change of the current. So to get the absolute rate change of the current, we have to rearrange this formula. We're gonna put 2 pi r equal the electric field multiplied by the electric field over permeability free space multiply the number of turns per meter multiplied by cross section area. Alright, and now I can put the numbers into the formula. We know this 2 pi multiplied by the radio, that is 0.0500, multiplied by the electric field, that is 1.20 10 times -5 over permeability free space, that is 4 pi 10 times -7 by the number of turns, 965, by the area, that is 4.00 10 times -4. All right, let's get that to the calculator. 2 pi multiplied by 0.0500 multiplied by 1.20 times -5 of 4 pi 10 times. Let me go back because I did it wrong. So I have to do it again. Sorry, I don't know what's happening with my calculator. So 2 pi times 0.0500 multiplied by 1.20 Did I do it right? Yeah, 10 times -5 over 4 pi 10 times -7 multiplied by 965 multiplied by 4 10 times. Wait, I did it wrong again. So 964 10 times -4. Alright. And this I get -7.77 amperes per second. Alright. Now we'll go with part E. So for part E, find the rate of change of the current in the solenoid if the electric field is in the loop at the point X 5.00 centimeters equal Y. Comma Y equals 0, comma Z equals 0 is vector of E equal to parentheses minus negative 1.80 10 times -5 vectors per meter close parentheses vector of G. Alright, so we're gonna use the same part Z, but electric field it's gonna be different. We know that it's gonna be E equal minus 1.80 10 times -5 volts per meter. All right, same as E. We change the electric field to 2 pi multiplied by the area, 0.0500, multiplied by this electric field that we're going to change here, 1.80, 10 times -5. All right, and then when it's the same thing, so permeability of free space multiplied by the number of turns, and multiply by 0.00, 10 times -4. So that in the area. All right, let me just right here and just get that to the calculator. So 2 pi multiplied by 0.0500. I don't know what's happening with my calculator. It's like crazy. I have to change it. All right, 0.0500 multiplied by 1.80, 10 times -5 over 4 pi, 10 times -7 multiplied by 965 multiplied by 4, 10 times -4. And I got 11.7 amperes per second. Perfect. Now, we'll go with part F. As I'm seeing here is the last part of this problem. So, for part F, a long solenoid has 885 turns per meter and a cross-sectional area of 2.70 centimeters. The current through the windings as a function time is 6.00 amperes per second squared multiplied by time squared. A wire loop of resistance 0.600 ohms is around the solenoid parallel with its coil and center on the axis of the solenoid. Where's the current induced loop at time equal 13.9 seconds. All right, we have the given data right here. The number of turns we know it's 585 turns per meter. The area is 2.70 centimeters square, and we change that to meters square, so 2.70 10 times -4 meters square. We have the resistance. It's R equals 0.600 ohms. Let's close it so it looks. All right, so time, it's 13.9 seconds. And we're going to use the current function. A equal 0.600 multiplied by times 2, and we know that it's 1 dt. Let's go to 1.20 times time. All right, the two formulas we're gonna use here, it's times the permeability of free space multiplied the number of turns multiplied by the area multiplied by the current section. So, and the other one, I'm a little confused right here. I'm sorry. So the induced EMF over the day. All right. First of all, we're gonna get the range of change. Let me use 1.20. That is what we got already. Multiply by time 13.9. Let's get to the calculator. 1.20 10 times 13.9 is 16 0.68 amperes per second. We're gonna use the induced EMF formula. Permeability free space 10 times -7 multiplied by the number of turns 185 by the area 2.70 10 times -4, and then we multiply that by the time that we already got that is 16.68. All right. And we'll pass that to the calculator. So 4 by 10 times -7 multiplied by 185 multiplied by 2.70 10 times -4 multiplied by 16.68. It's giving me 3.31 10 times -6 volts. Got it. Now, all right, now we're gonna set all the formula. Just to get the amperes, we know we got 3.31 10 times -6, and now we're gonna divide it by the OHMS. Yeah, I remember. So 0 so 600. Let's get that to the calculator. I'm gonna do it here, so I can square it. Let me use 3.31 10 times -6. 3.31 10 times -6 over 0.600, and I'm getting 5.52 10 times -6 amperes. Perfect. Let's double check the answers. All right, let's go to part A. 1,810 turns per meter, correct. Then part B, 7.7 10 times -5 volts per meter, correct. We got per C, 2.70 10 times -5 volts per meter, correct. Then long solenoid, part D, -7.77 amperes per second, correct. Now we'll go with part E. I got 11.7 amperes per second. That's correct as well. And for part F, I got 5.52 10 times -6 amperes. Incorrect as well. All right, Professor. Thank you so much. That was my exam, chapter 29 exam. Thank you.